Welcome to Under the Microscope, your go-to podcast for materials and nanoscience. I'm your host, Francesca, PhD in materials and nanoscience. With each episode, I introduce you to a scientist working in the field of materials and nanoscience. And we talk about their groundbreaking research, their career journey, their innovative discoveries, and their inspiring stories. We explore the fascinating world of nanoscience together. Today's guest is Francesca Calegari, a leading figure in the world of ultrafast science and Attosecond physics. Before we dive into the fascinating world of electron dynamics and her groundbreaking research, I want to take a moment to share why today's episode is extra special for me. Francesca is based in DESY in Hamburg. DESY is this national synchrotron of Germany. DESY. DESY is a very special place because during my PhD years, I attended my very first Women in Physics conference there, and it was organized by the German Physics Society. It was at that event where I met some incredible women in the field of physics, including Christiana de Moraes Smith, the female Brazilian physicist who went on to be the very first guest on my 42 question series and scientific twist on Vogue's 73 questions. I will include the link to Christiana's episode in the show notes, so be sure to check it out. And also, speaking of full circles, the Science Talk is now the official science communication partner of Quantor, which is an outreach project funded by the German Physics Society. So the Deutsche Physikalische Gesellschaft, which is DPG, and Quantor is part of the major project to celebrate the Quantum Year of Science and Technology 2025. It feels amazing to have come full circle in so many ways. I'm also curious to hear where you're listening from. So if you're tuning in, please take a screenshot and share it on your Instagram story or post it on LinkedIn and make sure to tag the Science Talk accounts on both those platforms. This definitely helps spread the word about the podcast and bring amazing materials and nanoscience to an even broader audience. All right, without further delay, let's get into today's episode. But first, a very quick word from our sponsor, Twitter Insights Pro.
If you've ever wanted to secure your Twitter archive, align your tweets with your evolving brand, or even repurpose your best content for other platforms like LinkedIn or Instagram, this is for you. With Twitter Insights Pro, you'll get a detailed, organized overview of every tweet you've ever posted, complete with visual documentation. It's an easy way to preserve your online presence and expand your influence. Check out the link in the episode description to learn more and take the first step today.
Please welcome Francesca Calegari, a professor at the University of Hamburg and also works at DESY. Welcome, Francesca. How are you?
I'm fine, and thank you very much for inviting me to participate in this podcast.
First things first, what is DESY? It's not a flower, right?
It's a facility that hosts the brightest sources operating in the X-ray spectrum range. They emit bright X-ray radiation. We have two main sources operating here, a synchrotron and a free electron laser. But in fact, I'm not using the synchrotron radiation, although I'm based at DESY. Sometimes I use the free electron laser, but we also develop our own light sources, very special light sources.
You're creating your own light sources. What does that mean?
We produce extremely short light pulses, and maybe I come back to the method to produce these very short light pulses later, because first I want to give you a little bit of excitement about why it's interesting to produce such ultra short light pulses. First of all, matter is not static, it's dynamic. Matter is constantly subject to external stimuli, including light or sunlight coming through our atmosphere and triggering a number of processes of biological or chemical relevance. the matter is responding in a very dynamical way. And from this dynamical response, the majority of the biochemical functionalities, for instance, are emerging. So in order for us to understand a specific function of matter, which could be, as I said, connected to biology, chemistry, but even material science, it's important to understand all these processes occurring at ultra fast timescales, because in fact, matter is reacting extremely fast to these external stimuli. To give you an idea of the timescales that we are dealing with, if you take a molecule, like a macromolecule that we have in our body, a protein, this molecule can fold and unfold on timescales that are microseconds. So we are talking about 10 to the minus 6 seconds. And then if you zoom into the protein, if you look into the subunits, you can have faster timescales in which these processes are taking place, from nanoseconds to picoseconds. And we're talking about now faster and faster fraction of a few seconds. And then, of course, you can zoom into the subunits and you can see that they undergo structural changes on timescales in the order of femtoseconds. Now we are talking about 10 to the minus 15 seconds, already extremely short fractions of These are not the fastest motions which are happening in the molecule. If you zoom even further, you find the fastest bodies, which are the electrons. In fact, electrons are the glue which keeps together the various atoms in a molecule. They create the bonds between the atoms, and they move even faster. They move on attosecond timescales. And now we are talking about 10 to the minus 18 seconds. So if you want to be able to capture or to catch the electrons, you need to be fast enough to see them, right? To do that, you have to use a trick, because our cameras are not fast enough to capture this motion, right? And therefore, we use extremely short light pulses to illuminate them on their own time scale, so in attoseconds. So we need to produce light pulses in the attosecond domain to be able to capture their motion. And I will explain how to do that. But first, it's very important. The message is, if you want to understand the functionality of matter, you need to be able to understand processes that are triggered by, for instance, the light-matter interaction that happens already at very early time scales that ultimately will evolve in your function at very long time scales. But it's important to understand these very fast time scales.
How does this work in reality? You can't observe with your naked eye. So do you use the slow motion, or what do you do? What exactly do you do?
So first of all, we have to produce these very short light pulses. And this is something that does not come for free. The limited number of laboratories in the world that are able to produce these isolated attosecond pulses, these extremely short light transients. And for that, we basically need high intensity lasers. We start from a laser which is typically commercially available, which is delivering femtosecond laser pulses, so in the 10 to the minus 15 domain. And then we need to use nonlinear optics. So we need to use the interaction between the lasers and the matter to produce even shorter pulses. And in fact, this is extreme nonlinear optics. It's called high-order harmonic generation. The discovery of this process has been awarded the Nobel Prize in Physics last year, so it was put under the microscope. And as it was a very important discovery, so with this extremely nonlinear optical interaction, where you focus your laser on, for instance, a gas target, you could produce radiation, which is, first of all, in terms of photon energy, more energetic than the initial laser. So the laser is operating typically in the infrared, and these high-order harmonics are produced in the extreme ultraviolet or even soft X-ray I was mentioned. So you can produce photon energies which are higher. And moreover, this radiation has shorter pulse duration. So we go from femtoseconds to attoseconds. Now we have these very short light pulses, which is wonderful, but we have to use them to image matter to make this ultra-fast movie that we were mentioning. And indeed, we need special cameras to do that. And the trick is actually the same as in the case of the flash photography. So maybe you have in mind these nice pictures of the rain falling on the ground, something that you typically cannot resolve with your eye or with a slow camera. because you will see only a blurred image of the rain falling on the ground. So you will not see the drop falling. You're not fast enough to resolve this motion. As we said, we need to be fast as the dynamics of the object in motion. And so therefore, the trick is, okay, I have a slow detector, like in my camera. So I keep my shutter open. The camera is acquiring, and it's very slow. But I will illuminate the object with light only in a short instant. So if I flash the light with very short flashes of light, then I will capture the object in a certain position. Then the object will change the position and I flash again light, and I will capture the object in the next position, and so on and so forth. And then you see the dynamics of a fast object, which is recorded by a slow camera, but with very short flashes of light. No, that's the trick of flash photography, or you see the dancer in all the possible positions during the dance, or the falling cat, or whatever. It is exactly the same trick. So we need basically the short light pulse to illuminate the object for, as I said, a very short instant that it's giving us multiple frames. Then if we record it at various time delays, as in the case of flash photography. But we need a triggering event. We need to trigger the dynamics in matter. And so we use a method which is widely used in the so-called time-resolved science, where we send the first light pulse to trigger the dynamics. So this will initiate the electron dynamics, for instance, in the molecule. And then we image it by sending a second laser pulse, which is our flash of light, like in flash photography. And what we image is, in fact, very different from a normal conventional camera, as normally what we do is that we ionize the molecular system, and then we look at the electrons which are emitted or the ions that are resulting from the fragmentation of the system. In a sense, we often destroy the system to look into its own dynamics, but we can repeat this for every laser shot, and then we can also change the delay between these two pulses. So you will have the first pulse triggering the dynamics, and then the second pulse is used to take the picture of the object at various time delays. And in this way, we can make a movie of what's going on in the molecule.
Okay, this is so cool. This is so very cool. And thank you very much for explaining it to me in such simple words. So you are sending two light pulses. The first one is to activate the electron or start the process, initiate the process that you want to capture. And then the second light or laser pulse is the one that is actually capturing the electron or the ion, depending on what you're studying. Help me visualize the outcome. Do you get a picture like on your phone, or what exactly do you get?
We use very sophisticated detectors, and we get very difficult signals to be understood at glance. So we need post-processing of the data. And in order to visualize a molecular movie in which we see all the electrons going around, or the structure of the molecule changing in time, we need to collaborate with theoreticians and theoretical modeling. So the experiment provides a lot of information about the process, but theory is actually then making these nice final movies, or putting everything together in a sense as they can then reconstruct how the dynamics is happening in the system originally, and helping us in visualizing nicely, as I said, how this glue, which are the electrons keeping the molecule together, are moving around in the molecular system. And so we benchmark theory, and the theory is helping us into visualizing how the dynamics is happening. So it's a very nice and cooperative way of producing scientific results with teams of experimentalists and theoreticians working together.
Please tell me about your career journey. Was like a 5-year-old Francesca saying that, oh, I'm going to work with the fastest cameras in the world. That's what I'm going to be doing, sitting in Hamburg. How did that happen? Tell me about your career journey, please.
I must say that my interest in science was triggered at the very early stage by my mom, who was giving me a microscope as a gift. We are not directly using microscopes, but in a way, this is a sort of microscopy as we zoom a lot into matter and its fastest time scales. I studied physics, and then it happens that I joined school of photonics, which was very strong at Politecnico di Milano. So in Milan, they did the effort of developing the first gating techniques to produce these very short, isolated attosecond pulses. We even had the world record of the shortest light pulses back then. And this was all very exciting because these were new light sources, opening the opportunity of investigating a new physics. And as a physicist, I was very excited because I thought, wow, we can really look into matter at these fast-time scales and looking what electrons are doing. And so it was all very fascinating. And then I stayed in the field. So I decided after my PhD to continue and to learn other techniques, mostly detection techniques that were very important to be combined with our light sources, as I said, to explore matter properly. And so I also was joining the group of Mark Bracking at that time at Amulf to learn about the velocity map imaging, the detection technique. I also spent 1 year in Hamburg, or a little bit less than 1 year, joining the group of Andrea Cavalieri to learn about RPs, so to explore different directions, different detection techniques. Mostly I was trying to combine, as I said, our ability to produce short light pulses with advanced detection technologies, really looking to advanced experiments and attempt to image these dynamics in complex systems. I got a permanent position as a staff scientist in the National Research Council of Italy, and I also got a European ERC starting grant, which was a very good start for my group at that time. And then I moved to Hamburg, where I got this position that I have now, and I could get more resources and establish my group, continue to push the boundaries for, as I said, exploring the possibility of controlling matter at the electron time scale.
Okay. This is really interesting. Thank you, Mother, for the microscope. Also, thank you for the plug or the wordplay with the microscope. You mentioned you started your science education and your PhD journey at Politecnico di Milano. Polyme, I think it is called. And I remember the second guest on Under the Microscope podcast, this was like 6-7 years ago, was Michel Celebrano. And he is working with nano antennas. And I can share the links of his podcast with you later on. And I can also put them in the show notes for anyone who wants to listen, because there is this connection as well. Wow, that is, and also congratulations, or rather maybe it was like a long time ago. So for you, it's like a lot more achievement since then, but also the ERC grant that you mentioned, the European Research Grant counts it, the Early Career Researcher, ERC. So it's that, right?
ERC is basically the funding agency or European Research Grant call. And then there are various stages. I got the starting grant, which is the first step. Then the next step is the consolidator grant, and then you are in the advanced. Now it would be more in the advanced category. So I will probably apply again, either advanced or synergy, which is another option. So there are various options depending on the career stage. But at the starting grant level is actually very important because it's a substantial amount of money that you get to start up your group, which is not so common, right? Because you're young, you want to hire people, you have ideas, you want some expensive instrumentation. And the ERC is really helping in that, especially if you are located in places where you don't get big startup funding. In general, it's never happening until you get the chair or something, right? So having these kind of startups is very important at the young investigator level.
Yeah, absolutely. And you also mentioned you also spent some time in Amolf in Netherlands. We have also had, I think, 2 or 3 guests from Amolf. Said Rodriguez, he works with the noise, and we also had a PhD student from Amolf. So I feel like the more people I talk to, the more scientists are featuring on Under the Microscope. With every passing episode, every new episode, I see there are so many connections in the world is so small in a way. It's really interesting for me as a material scientist who has a podcast now. So it's just quite interesting for me.
Quick break from the conversation. Just a reminder about Twitter Insights Pro. If you're looking to protect your Twitter history and make sure your brand stays consistent across platforms, this is the solution. With our service, you can easily download, organize, and repurpose your Twitter archive, turning your old tweets into new content for LinkedIn, Instagram, or even newsletters. Want to know more? The link is in the episode description. Don't miss out.
Okay, let me ask you this question, Francesca. It sounds to me already your current research is super interesting, and the research projects that you're working on are super interesting. You have been working on some really cool research projects over your career as a scientist. If you have to pick one research project that you're most proud of, or the most fun or quirky one, could you pick one research project and explain it to us in simple words in the section we call In Other Words?
I partially already explained it, so I think we have
Ah,
an easy way out here. But maybe I will add some more to it. I was, of course, very proud of this work we have been doing in the aromatic amino acids. So this was like the very first time that the Attosecond technology was used to look into systems that are complex systems. Amino acids for biologists, of course, are little molecules, but for us, these molecules with functional groups are very large for us physicists, and really trying to see that our technology can be used really to look into these ultra-fast electrodynamics occurring in such important systems for biology or chemistry was for me, I would say, a great achievement. Also because there were many skeptics. When I was saying that around the conferences that we wanted to push to study these biochemically relevant molecules, many were really saying, well, this technology is very complicated. You will not understand anything. Or there were many skepticisms around. So when we were successful, I think that was a great achievement. It was also acknowledged a lot by the international community. And our paper is heavily cited. I think it's very well known as an achievement. I think as of now it remains my main achievement. Of course, we are progressing a lot, as I said. And what I'm very proud of the technology of my group is actually that the study we have been conducting in aromatic amino acids was done with, as I said, extreme ultraviolet attosecond pulses, which is ionizing radiation. So this is well beyond the ionization potential of molecules. This radiation is interesting, but it's not penetrating our atmosphere, right? It's completely filtered by the atmosphere. So it's not, in fact, triggering the main biochemically relevant processes on Earth. So the spectrum of the solar radiation, which is penetrating the atmosphere, is indivisible, or for instance, the ultraviolet, part of the ultraviolet, portion of the ultraviolet. And the ultraviolet is triggering a huge number of photochemical and photobiological processes. So we are really concentrating now, and we've been very proud to produce the shortest ultraviolet pulses, not yet in the attosecond domain. So we generated sub-2 femtosecond UV pulses. This as of now, the shortest UV pulses used for measurements, and enabled a really new science, because now we are looking into these electronic processes in molecules triggered by UV light. So they really have a biochemical relevance. So no longer ionizing the molecules, but exciting the molecules with UV light, as it happens every day on Earth, in our skin or whatever. So really mimicking the realistic processes. So for that, I'm very proud, because my group was really pioneering this direction, and it's very acknowledged. I would say that now many groups are working in this direction, and I'm happy that I triggered the science.
that is really cool. And I can imagine why you picked this project as one of the projects that you're proud of. Let's go with that. Let's not underplay the other projects as well. This definitely is interesting, especially because when you started, there was a lot of skepticism about, yeah, it's not going to work. Why is it? But now, once you have successfully demonstrated that it does, its scientific relevance, now there is a new field or a sub-niche field that has opened, which definitely makes this project to be spoken about in our special section. Francesca, it's quite evident to me, and I'm fully convinced that you love the research aspect of being a scientist, because just the way you explain the science, how passionately you talk about the research and the science itself. So it's very clear to me that you love the research aspect of being a scientist. But there are other aspects of being a scientist, right? Especially a professor. So what else do you like about being a scientist? In addition to the research, let's not go into that, but the other factors that people are usually not aware of.
Yes. Yeah, indeed. As you climb the ladder and you go to the top, let's put it like this, then of course, also your job is changing a little bit. I must say that I'm no longer spending time in the lab, which is very sad. This is what I don't like. But at the same time, I got to do many other things as a scientist, and of course also getting more responsibilities and having different roles in the scientific community, which are very important to me. That I like also very much. What I like in science generally, besides the research, is the possibility to connect at the international level. I would say without biases, without any limits, and I think that's wonderful of the scientific community. So that we have a great international community. We get to travel, meet with people of any nationality, any background. And this is great. And this is happening since the very early stages of the career up to the top of the ladder. So that's wonderful. And that keeps going in a way that I really love. And I think there are only a few jobs in the world like this one that are really enabling us with this wonderful international community and connections. Besides that, now I'm having responsibility roles that I also like very much. So at first, I am the head of the scientific committee of PEER. PEER is our partnership for innovation, education, and research in Hamburg. So it's a partnership between Hamburg University and DESY. And I have the pleasure of heading the scientific committee, the scientific board, and take decisions and act for this wonderful cooperation between DESY, which is a national lab, and the university, because we need a lot of links between the two, as I said, in the various aspects. Of course, I'm a professor of physics, so this is also wonderful that I get to be constantly in contact with students. I get to teach. This was very important for me. I think it's really a gift, the possibility of teaching and of transferring knowledge, potentially have an impact on the education of students. And I'm training them mostly on ultra-fast lasers and what we do here, but I also enjoyed in the past training on basic physics. Education is very important for me, and I really would fight to stay in education. I would not give it up to teach, because it's very important. And last but not least, I'm also one of the directors of the Cluster of Excellence Advanced Imaging of Matter. So this is the Cluster of Excellence are actually initiatives funded by the federal government in Germany. So many institutions are working together on the same research task. In this case, it's the advanced imaging of matter, very broad topic. And the institutions that are clustering here in Hamburg are Hamburg University, DESY, Max Planck, and the European XPEL. Altogether, we work on the most advanced experimental and theoretical methods to image matter at all length and time scales with a very broad portfolio. And one of the three directors of this cluster, and it's a lot of fun to get to see how the cluster is evolving, the amazing science we are doing work together, and organizing and the training for the students, and looking into the developments also in terms of diversity and many other aspects to improve the quality of science on site. So this is generally very exciting. And we'll see. We are going under renewal now. We'll see if we'll be able to continue. As of now, it has been a wonderful experience.
Wow. Okay. There is a lot that you're doing. So not just the research, but you're also doing 50 zillion other things, which are also exciting and important. You're absolutely right. The more you progress in your career, the more impact you can have, because then you are you're on the board, or you're leading certain clusters, or you're leading certain initiatives. So this is really interesting. And it's also, for me, it's interesting to know, of course, in theory, I know that as a professor, as a leading and a senior professor with such amazing scientific impact, you do have different responsibilities. So it sounds to me, Francesca, your research experience has been wonderful. Of course, I only got the highlight reel over the last, let's say, 1 hour or so. But if you had 3 wishes to improve your research experience, what would you ask for? And I'm not promising anything here, okay? Don't put me under. Yes.
The gene in the bottle. Well, there are a few things that, more than a few things that, of course, would help a lot in improving science in general, the research environment. My first wish would be that we always have constraints with funding. Funding scientific research, especially experimental research, is very expensive. I came from Italy to Germany, of course, that's already the difference in terms of funding. I got a lot of funding via the program that I entered earlier, and generally I'm not complaining about funding, but I see that in time we are going more and more towards topical call, or so to say, where the society, what we believe as an immediate societal impact, or what we believe are the hot topic for the society now, which is wonderful. Certainly we need boosts in certain topics, which now is energy, quantum computing, whatever. But I see more and more that we tend to basically adjust our science depending on the topic of the call. So we have to somehow enter the scheme and be able to apply to get the money for a topic and call on a specific topic, which is not super nice, because I think sometimes as we orient or target our research over a specific topic, we lose the freedom of studying new things that accidentally could turn out to be even more important for those topics than what we originally planned. So I think the freedom of science and research is very important. And actually, maybe the ERC is one of the few funding lines that still survived with a completely openness in terms of topics. You can do whatever you want. You're not asked to do anything specific. And I hope this is continuing and even influencing other funding agencies to be more and more open. Although, of course, I understand with the shortness of funding available, as we are also navigating not a wonderful period or historical moment, one has to take decision of what can be funded. But at the same time, we need freedom as scientists. That's very important. And that was working so wonderfully for a very long time. And I think we should continue along those lines. That would be my first wish. Then, of course, there's the topic of diversity. Being a woman in the academic environment, I am trying to act as a role model, of course, and to try to improve diversity, and I even acted as a diversity director in our cluster and participated in many events and initiatives to promote the participation of female scientists in academia. But we need to improve those numbers. There's a lot of work to be done, and as a woman, you never know if you are in a certain position because you are a woman or because you are good. And I think we need to go beyond this feeling. Otherwise, it means that we haven't succeeded. And this is actually a shadow that we always have, right? As a male colleague, I'm here because of it. They wanted me to be here. But as a woman, you always ask yourself, okay, they picked me because they needed a woman in the committee. They picked me because they needed a woman director. They picked me because they needed whatever. I think it's a general feeling. Here in Hamburg, I have to say, I found a wonderful environment, and I rarely feel this. But anyway, it's always a question that is around, and this is because, unfortunately, of the situation as we are now, to still questioning ourselves on this topic, as we are not all equal, I would say, yet. Mm-hmm. And it's not only about women, of course. Diversity is a very broad topic, so I would say I would extend it to many more cases. Third and last wish would be, I mentioned already, I miss very much the opportunity of staying in the lab, because unfortunately, yes, by progressing in the career, you have to change roles and duties. But I was very good in the lab, and sometimes I really wish I have more time for it. Maybe, who knows, in the future that will come true.
Absolutely. So diversity in the scope on more open funding calls so that research direction is not completely driven by the funding call, but also it has some room for spontaneity in a way that allow for the discovery of the undiscoverable organically and not always planned. And more time in the lab, of course, and diversity in science. Diversity in the world, I would say, would be great because you're absolutely right. So now I'm leading the science talk. I'm doing this independently, so it's a bit different. But until now, during my PhD or during my time in a corporate world, it always crossed my mind. Am I selected because I'm a woman or because I'm good? Am I invited to speak on the panel because I'm a woman or because I'm good? There is this constant shadow, as you mentioned, that is always there for women, which is something that men, fortunately for them, don't need to have. Yeah. But I have to say, though, that now that you are in this senior position, you have more power to implement these changes, the first and the second wish, and also the third wish, like spending more time in the lab, right? You have more power to make these wishes come true than me. I'm sure this will happen. I'm sure you will make your wishes come true. For sure. So, Francesca, this has been wonderful to know about you, more know about your life as a scientist, to know about your research, about your group and your career journey and everything. But before I let you go, I have one last question for you. And that is related to your curation weeks. Every guest on Under the Microscope also gets the keys to now Blue Sky account called Under the Microscope, the same name, for one entire week. So what can the followers of Under the Microscope on Blue Sky expect in the week that you're taking over the account?
Yeah. So I will probably talk more about my science, of course. I would be happy also to exchange with followers about what we can do and then what are the exciting new things that we are doing in my group. And this week will be the week of the Peer Day, where basically I talked about Peer as a partnership between Hamburg University and DESY. Every year we organize this event, one-day event, where we bring together all the scientists within this partnership. We talk about exciting science. We have the young investigators which have been funded by our program for their seed project, presenting their exciting results. We have also a lot of exchange about the excellence on campus, so our excellence clusters, initiatives, and the developments of new facilities, for instance, the upgrade of the synchrotron here, DESY, which we call now Petra 4, ultimate microscope, they call it, also in line with this podcast. So a lot of exciting things will be going on and updates about Hamburg research environment that could be nice to share with followers so that can be updated about our initiative. And we'll see, depending on the feedback of the follower, what we will talk about.
Oh, definitely. This all sounds super interesting. And also, I hope there would be like tons of electron movies or these movies that you are capturing. This would be awesome. So thank you very much, Francesca, for speaking with me. This has been wonderful. And now looking forward to having you on Under the Microscope account of Blue Sky. So thank you very much for your time.
Thanks to you. Thank you very much.
Before we wrap up today's episode, one last reminder about Twitter Insights Pro. If you're serious about securing your Twitter legacy, aligning your brand, or making the most of your content, Twitter Insights Pro has got you covered. It's simple. Download your archive, send it to us, and we'll take care of the rest. Make sure to check the link in the description to get started and take control of your digital legacy today.